The universe isn't obligated to make sense, but it does have rules that it must follow. In our everyday experience, we perceive three spatial dimensions and the dimension of time, all intertwined in Einstein's theory of relativity. However, recent theoretical frameworks propose the existence of extra spatial dimensions beyond our conventional understanding. This raises the intriguing question: could gravity operate within these additional dimensions? The concept of gravity is not a recent discovery. Its origins can be traced back to ancient civilizations. Early philosophers and thinkers pondered the mysterious force that made objects fall to the earth. In ancient Greece, for instance, thinkers like Aristotle contemplated the idea of natural motion, suggesting that objects move towards their natural place within the cosmos. However, Galileo's experiments with falling bodies challenged and ultimately overturned Aristotle's prevailing notion of gravity. While Aristotle posited that heavier objects fell faster than lighter ones due to their intrinsic properties, Galileo's meticulous observations demonstrated otherwise. Galileo's work paved the way for Isaac Newton's later formulation of the law of universal gravitation, which described gravity as a force acting uniformly on all objects, regardless of their mass. In 1687, Newton released his seminal work, the Principia, unveiling his law of universal gravitation to the world. This principle asserts that every particle of matter in the cosmos attracts every other particle, with the force between them being proportional to the product of their masses and inversely proportional to the square of the distance separating them. Newton's mathematical depiction transformed our comprehension of gravity, offering a structure to elucidate not only the falling of apples from trees, but also the movement of planets around the sun. This law of universal gravitation provided a mathematical framework to explain not only terrestrial phenomena, but also the motion of celestial bodies. Newton's gravitational laws, while profoundly influential, did not provide a complete explanation for why all objects attract one another. This gap in explanation remained a point of contention and curiosity for physicists in the centuries following Newton's work. It wasn't until the advent of Albert Einstein's theory of general relativity in the early 20th century that a deeper understanding of gravity began to emerge. In general relativity, gravity is fundamentally simple. At its core, it revolves around the interplay between matter, energy, and the fabric of space-time itself. In Einstein's theory, gravity is not a force between masses, as described by Newton, but rather the result of massive objects bending the fabric of space-time around them. Matter and energy influence the curvature of space-time, which in turn dictates how matter and energy move. If you provide information about particles, antiparticles, and other energy forms, how space-time bends in response can theoretically be explained. As masses and energy interact, or as you, as an observer, move, space-time distorts accordingly. This curvature determines your motion and acceleration through the universe at any given moment. That's the essence of general relativity. Einstein's theory provided a more accurate account of the observed orbits of planets, the bending of light caused by massive objects known as gravitational lensing, and even the expansion of the universe itself. It introduced the notion that gravity is not merely a force acting from a distance, but an intrinsic part of the very fabric of the universe. Moreover, it emphasized that the larger an object, the greater the gravitational influence it exerts. It might sound strange, but the type of particle doesn't matter in general relativity. Whether it's matter or antimatter, massive or massless, fundamental or composite, it's all the same. The curvature of space-time dictates how everything moves, regardless of particle type. So when we observe a distant galaxy cluster, we understand that its mass bends space. And when we see light from objects within or beyond the cluster, even though light has no mass, it still follows the curved path set by space-time. There's an uncomfortable problem with gravity that's rarely discussed: its weakness compared to other fundamental forces. The apparent weakness of gravity can indeed be quite astonishing when we consider everyday experiences. Take a moment to observe your surroundings. Despite the immense gravitational pull exerted by the entire Earth, you can effortlessly lift your hand or even pick up a feather with just a finger. It seems almost paradoxical that a force capable of holding celestial bodies in orbit can be so easily overcome by the actions of our own bodies. This phenomenon is a testament to the nature of gravity and its relationship with mass and distance. When you calculate the forces between any two particles with mass, like electrons, quarks, or even composite particles like protons, you'll find something puzzling. Gravity, especially at small distances, is far weaker than the other forces. For instance, inside a neutron, gravity is over 30 orders of magnitude weaker than the other three fundamental forces. Why is this? No one knows for sure, but an intriguing proposal that dates back to 1998 suggests that gravity might be weak because it extends into extra dimensions beyond the familiar three spatial dimensions and one time dimension at very small scales, unlike the other forces. This idea posits that while the other fundamental forces are confined to our observable dimensions, gravity may spread out into additional spatial dimensions at very small scales, effectively diluting its strength compared to the other forces. In our daily experience, we're accustomed to three spatial dimensions: length, width, and height. These dimensions help us navigate and measure the world around us. However, Albert Einstein's general theory of relativity introduced a revolutionary concept: time as also a dimension, intimately linked with space. Together, these form a four-dimensional framework called space-time. Visualize space-time as a fabric stretching in all directions, where time and space aren't distinct but unified. This understanding of time as the fourth dimension is significant because it alters our comprehension of how the universe operates, especially concerning gravity. Traditionally, gravity was viewed as a force between two masses, such as the Earth and an apple, or the Earth and the Moon. Newton's laws described gravity as a force that pulls objects together. However, Einstein's theory revolutionized this perspective. In four-dimensional space-time, gravity isn't a force pulling objects. It arises from the curvature of space-time caused by mass and energy. Among the fundamental forces, gravity stands out as an outlier, being significantly weaker than electromagnetism, the strong nuclear force, and the weak nuclear force. This difference in strength isn't just slight, it's enormous. This raises the question, why is gravity so much weaker than the other fundamental forces? If all these forces are part of the same fundamental framework of the universe, shouldn't they be somewhat comparable in strength? The idea that gravity might suggest the existence of more dimensions emerges from attempts to explain its relative weakness and its peculiar behavior. Imagine standing at the bottom of a large swimming pool with a current flowing through it, gently pushing you along a path. However, from your perspective at the bottom, you only see the ripple caused by the current on the water's surface, a faint shadow or slight distortion, but you can't see the current itself. In this analogy, the gentle push of the current is like gravity. It's so weak that we can't even detect its full extent or see its shadow. This illustrates the challenge we face in understanding gravity completely. We experience its effects. Objects fall, planets orbit, but it's akin to feeling the push of the water current while standing at the pool's bottom. We sense the force, but our view is limited. We only perceive a part of a much larger and complex phenomenon. Just as the pool's current extends beyond what's visible on the surface, gravity might have aspects beyond our four-dimensional perception. Imagine a star emitting light in all directions. As you move away from the star, the light spreads out uniformly in a spherical pattern. The farther you are from the star, the dimmer it appears. This occurs because the light is distributed over a larger area as it travels away from the star. To grasp this concept, think about the surface area of a sphere, which increases as the square of the distance from the star. As light propagates outward to greater distances, its perceived brightness decreases proportionally to the inverse square of the distance. This principle extends to other forces such as gravity and electromagnetism. Similar to the dispersion of light from the star, the strength of these interactions diminishes as you move farther away from their sources. For instance, the gravitational force between any two masses weakens as the distance between them increases. Likewise, the electric force between two charged particles follows the same pattern. Essentially, these forces exhibit a spreading effect, causing them to weaken as they propagate through space. Now, let's consider a hypothetical scenario. What if we inhabited a universe with fewer than 3 spatial dimensions? How would phenomena like the spread of light, the decrease in gravitational strength, and the attenuation of the electromagnetic force alter with distance? We can experimentally explore this concept in condensed matter systems that restrict phenomena to surfaces, 2-dimensional, or even lines, 1-dimensional. In a 2-dimensional scenario, phenomena would propagate in a circular manner, causing their strength to decrease linearly with distance. In a 1-dimensional scenario, there would be no spreading out, so the strength of the phenomena would remain constant regardless of distance. While it's most evident with light in scenarios like 1-dimensional fiber optic cables, many physical effects and phenomena can be constrained to fewer dimensions rather than spreading freely through all 3 spatial dimensions. When signals are confined to fewer directions, they lose strength more gradually over distance. Consider this. In more dimensions, signals weaken quickly, but in fewer dimensions, they weaken more slowly. This pattern continues until we reach 1 dimension, where signals don't weaken at all. This pattern arises due to the spreading out of energy or information across more dimensions in higher dimensional spaces, causing signals to dissipate more quickly. Conversely, in lower dimensional spaces, there are fewer directions in which the signal can spread, resulting in slower weakening. Now you might wonder, how does this relate to why gravity is so much weaker than other fundamental forces? The concept of large extra dimensions comes into play here. Proposed in 1998 by Nima Arkani Hamed, it suggests that there might be extra spatial dimensions beyond the ones we know. These dimensions could be large compared to the Planck scale. According to this idea, while the other fundamental forces spread out only in our familiar 3 dimensions, gravity might spread out in these 3 dimensions as well as any additional large extra dimensions, if they exist. Before you argue against this, consider that by 1998, we already had experimental evidence regarding the behavior of the 3 quantum forces. Particle colliders like Fermilab and LEP had probed scales down to about 10 to the power of -18 meters, showing that these forces spread out only in 3 dimensions at that scale. Since then, the Large Hadron Collider at CERN has improved these constraints further, down to 10 to the power of -19 meters. If there were any extra dimensions that these forces experienced, they could only exist at distant scales smaller than these. However, detecting gravitational effects at similarly small scales is incredibly challenging due to the weak nature of gravity. By 1998, laboratory experiments had only probed the force of gravity down to scales of about a millimeter. This means there were 15 orders of magnitude to explore, ranging from millimeter scales down to atometer scales. If there were 1 or more extra dimensions where gravity could spread out, while the other forces couldn't, this could explain the more than 30 orders of magnitude difference we observe between the strength of gravity and the other forces in our everyday world. However, the uncertainty didn't last for too long. New experiments, including ones using microscopic force probes and optically levitated microspheres in a vacuum, showed that gravity followed the familiar Newtonian-like force law down to scales as small as microns. This demonstrated that the gravitational force does not spread or leak into extra dimensions at these smaller scales. However, there are concerns to consider. If there are large extra dimensions in nature, remember, large means bigger than the Planck scale, around 10 to the power of -35 meters, they could lead to the creation of microscopic quantum black holes or Kaluza-Klein gravitons at sufficiently powerful particle colliders. The absence of such signals at the LHC has limited the energy scale of any potential extra dimensions to be above about 6 TeV. Additionally, observations of gamma rays from neutron stars, such as those made with NASA's Fermi-LAT instrument, provide further constraints. These observations exclude scenarios with just one large extra dimension. Currently, the most robust limits on the size of any extra dimensions come from precise molecular spectroscopy. These measurements indicate that the size of these dimensions, as influenced solely by gravitational forces, must be less than approximately 0.6 microns. This corresponds to an energy scale roughly 100 times higher than the electroweak unification scale. This finding undermines the initial motivation for large extra dimensions, explaining why gravity appears so much weaker than the other observed forces. Before the Large Hadron Collider era, particle physicists were hopeful that discoveries beyond the Standard Model, such as new fundamental particles or interactions, would be uncovered. The large extra-dimensional scenario was attractive because it suggested that modifications to the theory allowing gravity to extend into these dimensions could explain gravity's weakness and predict the appearance of new particles at LHC energies. With the lack of fundamentally new particles or interactions emerging from existing LHC data, the hope for discoveries has diminished. To stabilize the scale of these purported extra dimensions, a new theoretical framework is needed. This means introducing additional types of new physics beyond just hypothesizing the existence of these dimensions. It becomes even more challenging if one wants to incorporate new physics, like dark matter, into these extra dimensions. Dark matter would need to exist in these dimensions without overlapping with our observable three spatial dimensions. However, its gravitational effects would have to leak into our dimensions, allowing dark matter to clump together as observed. This complexity is why physicists consider the number of new, free parameters introduced when discussing beyond the Standard Model ideas. A good idea in theoretical physics offers significant explanatory power with only a few new parameters. For example, dark energy, with just one new parameter, can explain various observations, including the accelerated expansion of the universe and spatial flatness. In contrast, the scenario of large extra dimensions requires introducing multiple new parameters to avoid conflicts with existing measurements. The major challenge for any new theoretical idea lies in its ability to address unanswered questions while maintaining consistency with what we already understand. We don't simply speculate about the universe without reason. Instead, we examine both known and unknown aspects, asking, will a new modification or addition to the theory explain something currently unexplained? Will this modification disrupt what we already understand and can explain? Many successful new ideas emerge with just one additional parameter, but they often require theoretical gymnastics to survive scrutiny. The concept of large extra dimensions initially held promise to explain the weakness of gravity while predicting new particles. However, with current constraints, this modification alone can't explain gravity's weakness and faces various challenges: stabilizing the size of extra dimensions, absence of proton decay, lack of discovery of Kaluza-Klein particles, dependence on hidden sectors, or non-standard model states. These issues cast doubt on the viability of the large, extra-dimensional scenario. While nature may surprise us with new complexities, this idea remains speculative until direct evidence supports it. Well, we've covered a lot in this video. One thing worth noting is our evolving understanding of gravity. From old ideas to new theories, it's been quite a journey. Now, considering extra dimensions adds another layer to our thinking. It may be a bit complicated, but with time, scientists will be able to provide a definitive answer to this topic. And that's all for this video. I'd love to hear your thoughts in the comments. Thanks for watching, and check out this video, where we talk about how black holes cause dark energy.